Good afternoon, everyone. My name is Jennifer Van Ostrin, and on behalf of ACRL and Choice, I'd like to welcome you to today's program, Lessons from the Maker Movement, sponsored by McGraw-Hill Education and featuring Donald Norris. Today's discussion is one in a series of sponsored webinars from ACRL and Choice that addresses new ideas, developments, and products of interest to the academic library community. Free to users, these structured 60-minute live presentations provide the opportunity for interactive discussions of important new issues and developments in academic librarianship by librarians, vendors, authors, and other interested stakeholders. Before we get started, I'd like to point out a few features of the webinar software. In the main area of the screen, you can follow along with the presentation materials. Along the left-hand side, you will see a Q&A panel that you can use to submit questions or comments. Please feel free to submit these throughout the program. And finally, please note that today's program will be recorded and all registrants will receive follow-up instructions on how to access the archived version. And now for some background on today's speaker. Donald Norris is an electronics engineer with an advanced degree in production management. He has more than 12 years experience as a professional software developer using C, C#, C++, Python, and Java, as well as 5 years experience as a certified IT security consultant. Don has written 3 books for McGraw-Hill, including Raspberry Projects for the Evil Genius, Build Your Own Quadcopter, and Internet of Things, Home Automation Using the Raspberry Pi, Arduino, and Beaglebone Black, with a 4th to be published this summer, Programming the Intel Edison. He is an avid electronics hobbyist and maker. With that, I'd like to turn things over to Don.
Well, thank you, Jen. Appreciate it. And good afternoon or good morning, depending upon which time zone you're in. We'll get started with our presentation today on undergraduate engineering projects using microcontrollers. So let me get it going here. There we go. But before we actually start, I have some questions I'd like you to answer, which appear in the top. Does your school, your institution have an innovation lab or a makerspace? And if so, where is it located? At the general library or in a specific school? And finally, do you incorporate any discussion regarding open source versus proprietary software in your curriculum? Open source is an extremely important topic in today's software development world. So we'll get that working right now. And I can see that the answers are coming in pretty well. So I think we can start our presentation. Okay, first of all, what is a microcontroller and why should you even care? Well, basically a microcontroller is simply a computer system that is embedded. All right? Embedded means it doesn't have a human interface setup. There's no keyboard, there's no display in its normal operation. However, for development purposes, and there will be a few microcontrollers I will discuss that do have the capability to have a keyboard and a screen associated with it. But usually this is only done during the development phase, not during the deployment phase. Okay, so a microcontroller is, you can think of it as a specialized computer system. You interact with microcontrollers every day. Your car engine probably has at least a dozen of these microcontrollers embedded in the engine, doing various things from engine timing, oxygen sensing, all these other features which are necessary to control today's modern engine. Okay, why do we even, are we concerned with microcontrollers in today's education, especially for our engineering undergraduates? Well, they're an essential skill, an essential item that undergrads must understand. They're used in most modern systems. They provide the intelligence and the communication behind most consumer and industrial products that are manufactured in today's world. Engineers which are not comfortable or are conversant in this technology will definitely be at a disadvantage when looking for employment or seeking to improve their existing opportunities. So it's important for them to understand that knowing how what a microcontroller is and how it works is an extremely important skill in today's world. They're not just for computer science and EE majors. They are for all the engineering majors and non-engineering majors too, which will be involved with this. I teach at a school which is basically a business school, but we do have an information technology department and a computer science specialty too. So we are heavily invested in microcontrollers. To be an effective team member, developing a product or system that uses these controllers, you've got to know what's happening with them, how they work in the system, and the various aspects of it which you need to know in order to develop it and integrate it properly into a system. Basically, the pros and cons of using microprocessors, microcontrollers. All right. What about projects? Well, the previous few slides were just some justification on why these projects these microcontrollers are important for all engineering majors. Projects are just one tool along with all the other tools that are used in engineering colleges and universities to promote and create a good education for our undergrads. But projects do have a significant difference. And this difference is that the students can experience firsthand the results of their labor, whether it be successful or not. And that's important to try. Hopefully they will be successful, but sometimes, and you'll see in a later example in a slide, they're not successful. But that doesn't mean that students don't learn. They do. I have 5 goals for any student project. These are mine. A project should first be informative and educational. Secondly, it should hold their interest. It should be interesting, whatever it be. Third, it should be topical. In other words, it should use current technology, nothing that's kind of outdated. Fourth, it should be affordable. And fifth, it should be doable within a reasonable time frame. I consider a semester a reasonable time frame. Some projects could span a couple of semesters, but usually no more than that. And having a time limit is an important aspect of a project, and we'll talk about that in a moment. I do have a question. I think that's going to be posted about if you have your own goals. So I would appreciate if you would want to add your input, and we can address that at the end of the presentation. So having established what the microcontroller is in general, I'm going to talk about a few controllers which are in wide use today, especially in the maker community. The ones I discuss are those ones I actually had my students work with in their own projects and that meet their goals and requirements. And without further ado, the first one is the Raspberry Pi. And I'm sure most of you have heard of this board before. Before I get into some of the details, let me see if I can get this working here. Here is point out a few things about the Raspberry Pi. First and foremost, I just put the pointer on what they call a SoC, or a SoC, a system on a chip. this is the, shall we say, the brains of the microcontroller. It's a computer. This one is made by the Broadcom Corporation, a UK company that actually is a very big manufacturer of cell systems, things that go with your smartphone. It's called the system on a chip because it contains 3 items. It contains the actual CPU, central processing unit. It contains memory, dynamic RAM memory. This is memory which holds data that's actively used during the computations. And it has what we call a GPU in there, a graphics processing unit. And it's a very powerful graphics processing unit, and it will actually handle high definition video. Let me point out a few other items on here before we proceed too further. This can right here is a top view of an Ethernet connector, allowing this board to connect to the internet through a LAN. And I failed to mention that this board is actually a view of the latest Raspberry Pi. It's called a Model 2 on their B version. It has 4 USB ports. There are 2 ports stacked on top of each other right here. It has this is what they call a FTDI controller. It's basically a USB controller. It has a full stereo output right here. This is a top view of an HDMI connector. So this is where the video would come out of this board. This is a micro USB port here, which is used for power. And this here and this item right here are 2 what we call flex connectors. This one is used for the camera, what they call a Pi camera. This one here is used for what we call a Pi display. That has not actually been issued by the company yet, or the organization, and I'll get to that in a moment. That should be coming out very, very soon. The camera, which plugs into here, has been around for about a year. So the Model 2 is pictured, and it is the latest in a series of units that were first introduced in 2011 by the Raspberry Pi Foundation, which is a UK charitable trust. They were created for the education, computer science education of high school students and even primary school. It was designed to be extremely low cost, and believe it or not, they have kept the cost constant over the last 4 years of being produced. The Model 2, which is the latest version, is $35, which is exactly the same price that the original Model B was introduced in 2011. Interestingly, the Pi was only estimated to sell about 10,000 units. However, at the end of 2014, over 5 million units have been sold. There is a huge infrastructure created around the Pi with many, many thousands of open source developers. That means there's a lot of support for the Raspberry Pi. Just call it a Raspberry Pi from now on. Here's my next processor I want to talk about, and it's called the Beaglebone Black. It's actually produced by the Texas Instruments, or TI Corporation. Now, the Beaglebone Black is an interesting processor in the sense that it's the same type of processor that the Raspberry Pi is, in the sense that it has a CPU, and unlike the Raspberry Pi, this one, let me just put it over here. This is a CPU. This has an external memory. Now, what I failed to mention previously about the Raspberry Pi is that the Raspberry Pi needs external, shall we call, secondary memory, or kind of a permanent memory for its operating system. It uses what we call a micro SD card, which plugs in under the underside of the board. I didn't have a picture in the previous slide, but it's just a micro SD card, standard micro SD card, and plugs in there. And that's where you put the operating system on all the software. Okay. For the Beaglebone Black, they have a separate chip, so you do not need an SD card to store the operating system for this particular board. There is an SD card holder on the back side of this board, but that's for additional memory. Okay? And then there are some other things here for this holds the dynamic RAM. Interestingly, this is 512 megabytes. The Raspberry Pi has 1 gigabyte of memory, so twice the dynamic memory of the Beaglebone Black. And here is the Ethernet connector, and here's two USB ports on this side, and there is you can't see it easily, but there is what we call a micro HDMI connector right here, and that's where you get your video out. And this is a 2.1 millimeter barrel power connector. You can connect what we call a wall wart, that thing that plugs into a wall, power supply, and it takes from 7 to 15 volts on to power it up. Some interesting items about the Beaglebone Black. It was the latest in a series of Beaglebones that were introduced by TI in 2009. Like the Raspberry Pi, it supports full Linux. And I make the statement here, there are different Linux distributions that are quite similar in functionality. Well, that's changed just recently because the Beaglebone Black Red C comes with a full-blown Debian Linux distribution, which is exactly the same one that comes with the Raspberry Pi. Why this is important is that a lot of people, a lot of students, a lot of developers are very comfortable developing using the Debian Linux distribution, and it's a very, I should say, fairly easy operating system to master. And there's a ton of supporting software available for it. The Beaglebone Black is a bit more expensive than the Raspberry Pi, and in my opinion, it doesn't seem to have as large a support infrastructure as the Raspberry Pi. However, it is highly capable and has actually some more features than the Raspberry Pi has. Technically speaking, I won't get into in a lot of detail, but these microcontrollers are all designed to work with all sorts of sensors. The Raspberry Pi does not have what we call an analog to digital converter built into it. There are a lot of sensors which are what we call analog in nature, and their signals have to be converted to a digital format to be processed by the microcontroller. The Raspberry Pi needs an external chip to do that, but the Beaglebone Black has that capability built into it, which is a significant difference. Also, that the Raspberry Pi needs the external SD card I was talking about, where the Beaglebone has that built into it. If you consider the cost of those external items added to the cost of the Raspberry Pi, you'll find out that the cost of the Beaglebone and the Raspberry Pi are almost identical, about $50, $55. Now we come to another board, which is called the Audrina. And the Audrina is actually significantly different than the Raspberry or the Beaglebone Black. All right, it actually has less capabilities because its processor, which you can see, just barely see in this photo here, is right here. It's called the Atmel 328P. And it is much more limited than either the Raspberry or the Beaglebone Black. However, to compare directly the Audrina with the Raspberry or the Beaglebone Black, it's really an apples to oranges comparison. They're really kind of different features and different applications. I do want to point out this to you. You see these sockets here on either side, top and bottom? They're designed to hold what we call Audrina shields. And there's a whole slew of these shields available that plug directly into the Audrina and extend its capabilities from specialized sensors to communication. You notice that there is no Ethernet connectivity with this board. There is a USB host connector right here and a power connector right here, and that's it. Other than these, we call them GPIO, general purpose input output connections right here. The Audrina, and the one that's shown here is the Uno R3. It's been around for quite a while, 10 years. First introduced in 2005. It is completely open source and it has a very large infrastructure. It's been around for a long time. You can see down in the web links, Audrina.cc, and that is a clue to you that it's actually been developed in Italy. That's where the development center is. The Audrina differs significantly from the Raspberry and the Beaglebone Black because it needs a separate computer to develop software on. There is no organic operating system running on the Audrina. Okay, but that's because it has a slightly different purpose than either one of the previous microcontrollers. It's designed to be a truly embedded system that once you program it and once you get the sensors working and what you need to do and what you want to control, that's it, leave it alone. Just plug it in and away it goes. It's low cost and it's very comparable to the Raspberry as far as the cost goes, about $30 to $35. And feel free to make sure you ask questions as I go along. I may be going a little bit too fast for some of the more non-technical viewers of the presentation, but that's, and I'll be glad to come back and cover on any questions that you may have. Here is the Edison. The Edison is, believe it or not, the smallest of all the microcontrollers that we talked about. You can see it compared to the Jefferson nickel right here. It's not a very large module. In fact, it is a module. You can't see on the back side of it, but there is a very, very small 70-pin connector which must be used to plug the Edison into a board. The Edison by itself, what you see right here, doesn't do much for you. It has to be plugged into some sort of support board. Okay, the Edison is a very new chip. It was just introduced by Intel in September of 2014. It's the smallest of all the microcontrollers, and like I say, it needs some sort of support board to function. Believe it or not, it has built-in Wi-Fi and Bluetooth connectivity. Its cost is slightly more expensive than a Raspberry, but it also has a full-blown Linux operating system running on it. The Edison right now comes with what we call the Pokey operating system, Linux operating system, which is which is an operating system that's been really designed for professional developers. Not as easy to modify or understand as the Debian distribution. That's the bad news. The good news is that a company called UB Linux has created a port to the Debian distribution, and it's not too difficult to overwrite the existing Linux distribution and put the Debian, which is exactly the same as the Raspberry and the Beaglebone Black. So, in fact, as Jen mentioned, a book I just wrote about the Edison is coming out this summer, and most of my projects are using the Debian distribution with the Edison chip. The support infrastructure is obviously quite small because it hasn't been around very long, and it's rapidly building for this module. So stay tuned. There's a lot to be seen about this Edison in the near future. This is the thing which I would talk about with the Edison, which would intrigue me about student projects, is that it's so small and it can be easily battery operated that you could create a series of wearable computers with this that can do all sorts of things. Again, in my little book that's coming out this summer, I wrote about a project which you could strap on Edison with a motion detector. Actually, I use what we call a 9-degree of freedom sensor. And you could actually put it on a patient's leg, and if that patient was infirmed and wasn't supposed to get out of bed and start walking without a caregiver nearby, this would send an alert over the Wi-Fi to a specialized website that would in turn to be monitored by a caregiver and alert them that the patient is on the move and probably should need attention. So wearables and medicine are hand in hand. I would be remiss in not mentioning other microcontrollers that have been around for quite a while. And the most venerable of them all is the 8051/8052 series. These have been around for over 20 years. And they are what I call the invisible microprocessors. They, like the Audrina, have to be developed using an external computer. They are put into industrial equipment, they are put into consumer equipment, and they are the invisible computers. They've been around for quite a while. In fact, I would, without hesitation, say that there are more 80, 51, and 52 series out there than there are all other microcontrollers combined. Intel makes this, and they still do make them, but they're not recommended for new projects. These new systems I was just talking about have far more capability. They are 32-bit processors versus these 8051s, which are 8-bit processors. So they have much less calculating capability than the old 8051s. The 8051s are around, and they will be around for a good number of years to come because of all the legacy products that exist. Okay, now let's change our focus a little bit, and let's talk about some more general topics about how projects should be done. Well, in my opinion, projects should follow the same kind of progression that they would be followed when the student graduates by a working engineer. Okay, first thing is that projects should be undertaken by teams. Industry doesn't really have too many places for lone wolves anymore. My suggestion is to have teams of 2 and not more than 3. I found that any more than 3, then it becomes a little bit hard to figure out what each student has done for the project, their contributions. All projects should start with a requirements phase. That's where students are expected to clearly understand the project goals and the expectations. Oh, you wanted me to have a robot that walked, and I made you a robot that swam. So there you go. You want to make sure that the requirements are clearly understood by the students and the teams. Typically, the artifact that's created from this phase is what we call a statement of requirements. This is kind of the contract between you and the student saying, okay, this is what the expectations is, and this is what I will accomplish. Also, there should be a realistic schedule created with appropriate milestones from which the project can be assessed, the progress can be assessed. That's key, and as many of you understand that most projects in industry fail because of unrealistic time frames, unrealistic goals. Okay, so it's important that students understand that they have to create a good schedule and appropriate milestones to know where they measure their progress. Okay. Also, a bill of materials is also a good idea to create. Sometimes you may need what we call a long lead item, an item which takes more than a day or two or a week to procure. And that has some significant impact on the completion of the project. Sometimes if the lead time is too long, then students have to realize that they have to do a redesign to maybe design out that long lead item and go another approach. Other times, maybe the project could be extended slightly to accommodate the long lead item. This is a key item that is done in industry all the time. So again, I want to expose students to what they're going to encounter in an industrial situation. Formal delegation of responsibilities is an excellent idea. So each student knows what they're going to do, what their contributions are, okay, and their expected participation. It's none of this business of, okay, I won't participate until the last weekend before the project is due. They have to participate on a continual basis. And also, students should not be shy about expressing to their fellow team members if they're having difficulties in meeting their responsibilities. Sometimes responsibilities can be shuffled around and teams adjusted to take account student strengths and weaknesses. And there may be other items as needed by the team to accomplish their goal. So now we're at a point where I'm going to show you 4 or 5 projects that I had my students build. This was my IT 475 class. It was a class named Trends and Technologies. It was basically an innovation class. First, a little bit of background about the course. I only had 9 students in there. Okay, so that meant I really couldn't break it up into my ideal teams of 2 or 3. So I felt that it was small enough that I could pay particular attention to each project and give my input and advice along the way. All right, and I had students submit their own initial proposal, which I reviewed with them and approved. I also told them they could change course, change the project during the course if desired. Believe it or not, most of them did that because they ran into things like long lead items. They recognized that perhaps the project they initially tried was a bit out of their comfort zone. They didn't have quite the background to handle it. So that's a good way of doing it, in my opinion. Okay. The first one was the RGB, red, green, blue strobe, using the Raspberry Pi. The student used the Raspberry Pi with what we call a pulse width modulator, PWM. It controlled 3 high-powered 30-watt RGB LEDs. And what I mean by high power, I mean you couldn't look at that when it was on full power. It was so bright. The student explained how he learned, what he learned about the PWM and how it was very suitable for precisely controlling high-powered devices. PWM, by the way, is used significantly in industrial situations for controlling for various devices like motors and lighting systems and things like this. He was going to try to pursue the project a little bit further after the class. I adapted it with his car. I didn't want to go into any further thing about, that might be a little bit illegal, but that was his call. And here is a picture of only one of the 30-watt LEDs running at full power. I don't know if you can see it clearly here, but this LED is mounted on an aluminum heat sink. It generated a lot of heat as well as a lot of light. And there's a Raspberry and some auxiliary systems behind here. He was quite pleased how this all turned out. My next project was a remote database using a Raspberry Pi. This project entailed basically setting up a what we call a MySQL database and remotely logging into it to retrieve data, and actually not just data, but audio and video. There was no additional software required for this other than the Raspberry and the normal peripherals, like the keyboard and the monitor, and I believe a stereo amplifier. The student successfully demonstrated it in the classroom. He wanted to include some media streaming so he could remotely access his music and videos. Here is not a screenshot of the students because that was kind of uninteresting. What I've shown you here is a screenshot of the what we call the XBMC application. XBMC stands for Xbox Media Center. This picture is an actual screenshot from running from a Raspberry Pi, and you can see clearly, well, I don't know if you can see real clearly, but this one here is a selection of different movies that are available. The Raspberry Pi will, in fact, stream HD video very nicely in stereo sound. So you can use it as, and many, many people do, use it as a extremely inexpensive media center. And it's so small that you can tuck it actually behind your television. And you can control it remotely using over the LAN or Wi-Fi. My next project I included because I wanted to show you a project that didn't actually work. The student wanted to create what we call a chat server. His student's a big gamer, and he wanted to create a way of inviting his friends into chat sessions and discuss those and various other interests. Unfortunately, because of a variety of instances, and I won't get into all the nitty-gritty details, he could not show me the complete project. He did show me his work in progress, but from what he showed me, I was absolutely convinced that he would eventually stand up a workable chat server. The takeaway from this is failure is always an option. Sometimes you have to understand that for whatever reason, you have to cut your losses and go on to something else or change your approach. I didn't fail him for this. He got a passing grade. And I hope he gained some valuable experience in trying to do this project and recognizing the difficulties that can occur unexpectedly. So that's another aspect, another takeaway you should understand from these projects. This project used an Audrina. Okay, one of my students was very comfortable working with the Audrina and chose to do a simple project where the Audrina would sound an alarm if a motion sensor were triggered in a room. She used a passive infrared sensor, what we call a PIR, connected to the Audrina that also had a buzzer attached to it. The project worked successfully. Okay, and that was it. It clearly demonstrates that all projects don't need to be cutting edge, nor do they have to be complex. They have to be achievable. I mean, if she did well, this wasn't, I wouldn't call this a A-level project, but it was definitely a good project, and she learned a lot about the Audrina and how to effectively deploy it. The last project I'll talk about is the Pi camera. And remember I showed you those little connectors on the Raspberry Pi board? He connected a Pi camera onto those, and it was worked very nicely. And there's a lot of software that comes canned that you can just load into the Raspberry Pi, and it works right out of the box. He demonstrated both still pictures and videos he had taken with the Raspberry Pi, and he also demonstrated some software scripts he created to control for how he took still frames and videos. It was an impressive project, and it amply showed the Raspberry Pi's multimedia capabilities. And by the way, the Pi camera, which is, I believe, 5 megapixels in resolution, is only $25. Not bad for a still camera and a video camera. So, in summary, most projects were successful. Some of my projects were partially successful, and one, as I showed you, didn't function at all. All students learned from their efforts and experiences while working on their projects. The experience they gained hopefully will dovetail nicely with classroom discussions. I occasionally offered my guidance and suggestions, but the vast majority of the work was done by the students on their own. All students used some internet sites, looked up, obviously, some information. One thing I failed to do, and I wish I had, was I have them record which sites they use and what knowledge they gave from the sites. What I haven't shown you on this summary is I did create a blog and a wiki where my students could go and post questions to each other to help get over some hard spots. And on the wiki, they posted their progress, so I knew what was going on and wouldn't be a complete surprise at the end of the course. Some key points to be followed in project development. Students should work to industry standards as much as possible. They will greatly benefit from this approach when they're actually working with standards. How does that impact the libraries for you folks in the library area? Well, standards are not cheap. Standards are expensive, but engineering students especially need access to real-world standards, because these are the things that they have to develop their communications with, whatever aspect. So having standards available is a key feature, a support feature that projects should have. All projects should strive to have great documentation, not just average, but great documentation. I know engineers hate documentation. I know it. I've been one. I've done it. But we do need documentation, okay, including how the effort progressed. These are lessons learned that are important. I always want to stress about how teamwork is so very important in successful project completion. Lone wolves, again, are not encouraged in today's workplace. Summary: why undergraduate engineering projects are important. The undergrad should expect to gain experience in transforming their theoretical concepts into real-world physical systems. Okay? They will encounter trade-offs, which I talked about earlier, between what is desired and what is practical, considering both schedule and cost. Remember the long lead time items. Okay. Students should be thoroughly engaged in applying what they are learning to a demonstrative project. In other words, they have a practical result. And hopefully, and not least importantly, they should have fun with their projects. Where do you go from here? Well, there's an excellent website, and it's listed in the web links. I just wanted to make sure that you knew about it. librarymakerculture.weebly.com. It's a great website, and there's also, it's done by the University of Michigan, and thanks for anybody who happens to be in the webinar from that school. I would highly recommend that you go to this website. I know my school, Southern New Hampshire University, is also a participant in this website. So definitely take it in. You'll find some very, very valuable resources there. Finishing up here, we have a new makerspace page being offered by the McGraw-Hill AccessEngineering Library. You can see the website right there. And here's a preview for you. Here's the token number, and there is the website you go to. You'll have a free 2-week trial of the AccessEngineering token. Now, I have gone to AccessEngineering. It's a very excellent site. There's a lot of good information, a lot of great resources available on this. And this is the last slide in our presentation. However, I do want to go into some questions and answering. I'm going to go over and see what's over in our questions and answering. So please feel free to type in your questions, and I'll try to answer them as best I can. All right, still waiting for some questions. We have about 12 minutes left, 11 minutes left in our allotted time, and that should be enough. Get some questions in here. All right. All right, here's the question I have. With something such as an Edison, could one create something like a wearable device that was hardwired to something like a strain gauge and also receive data wirelessly from another sensor? So that's the first part of the question. Let me answer that first. The answer is absolutely. You can create a wearable device. As I mentioned, I created in my book a patient movement sensor, and that uses a 9-degree of freedom sensor. A strain gauge, I'm not off the top of my head familiar with how to, I think you could do that with a strain gauge. In fact, I know you can. You can use a, what they call a piezoelectric strain gauge for certain. So there might be a little bit of interfacing involved, but you definitely can do that. And unfortunately, the Audrina needs a analog to digital converter, so that would have to be factored into it. But you can, there's a company called sparkfun.com, which is an open source provider, shall we say, and they provide all these stackables, shall we call them. You could plug a Edison in, you could plug in a battery pack, you could plug in an A to D, the analog to digital converter, and you can plug in proto boards where you can wire a interface to the strain gauge. Can you receive, part of that question was, can you receive wireless data from other sensors? The answer is absolutely. It has, the Edison has Wi-Fi and Bluetooth, so you can go either way. Can you do a wireless output to something like a smartphone? Absolutely, too. That's an easy thing to do. You can output to a Android or iPhone, depending on what your flavor is. Okay, other questions? I have a question here. Do you have prerequisites for your class? And again, my class was a non-engineering class, so I have to make that clear. Non-prerequisite I really had was that they had at least one programming course. At my university, we focus a lot on Java, which is an excellent prep for this. So yes, students should have some experience with programming, hopefully an object-oriented program like Java. Okay, let's see. Okay, question, and I'm not actually an expert on this, but I'll try to give you my best shot. Question is, we are looking at developing a makerspace in our engineering library. Are there some key things that we should include? Yeah, first of all, you need a 3D printer that draws people in right away. We have 4 3D printers in our innovation lab at my school. You need Raspberry Pis. You need workspaces, that means monitors and keyboards. You need Audrinos, that kind of stuff. So that's not terribly expensive. But I'll tell you what really you need. You really need some faculty or some mentors to help people along. It's not just to provide the material. You really need some good guidance. I created a series of videos and I gave some lectures in conjunction with my innovation space. So it's important that you have active, involved faculty to really make your innovation space a go. Another question, during what undergraduate year would projects be most appropriate in my opinion? I think they could be appropriate at any year. I think definitely you could include them in the freshman year, but certainly by the sophomore year. And the projects could become progressively harder or more complex as the curriculum goes on. I mean, in other words, a senior level project should be a challenge. It shouldn't be a fairly simple plug and go type of situation. Okay, all right. Is your library doing anything with makerspaces at this time? Yes, like I said, we have what we call the Innovation Lab. Go to that website I was talking to you about, weebly.com, and you'll see Southern New Hampshire University's innovation site. In fact, it's a great website. You'll see what other people are doing. You'll get a ton of ideas for your own library from there. And it's a good selling point, a good pitch for your administration. These things aren't cheap. You're not cheap, but you'll definitely be well worth the money. Okay. I'll answer this one about what is the name of the book that's coming out this summer. Actually, the working title is Programming the Edison. That might change a little bit. Like you've probably seen in this presentation, I do get a chance to get carried away a little bit. So the projects get a little bit in detail, so it's maybe a little bit more than that. But look for my name, and you can go on Amazon.com, and you'll see all my books. And actually, I have a author's page on Amazon, which I really don't, I would encourage you to go to and ask questions. And I love interacting and answering people's questions. It doesn't have to be about my books at all, to be on anything, and I'd be more than happy to try to help you out. I think that we are really close to the deadline. There are a lot of questions that are still in the queue. I don't think we have time to finish them off. I will get answers to your questions, and we'll follow up with some sort of post-session, and I'll let the fine folks at ACRL to deal with that. I will try to answer your questions. So I guess I am all done, and I thank you so much for your attention and your time here. And I hope I gave you a little bit of information and encouragement on this area. Thanks again.
Great. Thank you, Don. I just want to give Don a virtual round of applause for spending time with us today and sharing some great information. And just as a reminder to the participants, we have recorded today's program, so please be on the lookout for a follow-up email from us that will include instructions on how to access that archived version. And as Don mentioned, for those of you who have questions unanswered, we'll work together to get those answered for you. And thanks again to everyone for joining us. I hope you all enjoyed the session and have a great rest of the day.